So we're going to talk here. Exponential growth is typically, here's our objectives, outcomes. Use exponential growth model and applications, including population growth and compound interest. And you're going to see in the homework, there's several compound interest problems, and they typically take the form of how much would a person have to start with to end up with this much money as your goal. Also, you see your population growth tends to follow that exponential growth model. However, what it does, this is the logistics growth model. Your population will do this, where it reaches, and that's not for this. This I was hoping covered it and didn't. You reach a carrying capacity. Typically in a population. So, there's only so many resources. And so people talk about Earth and what are the resources on Earth? And I'm really digressing from the lesson here, but the people say we're reaching that limit is what Earth can carry. And I would actually argue, no, there's a lot of unfarmed land. If you had to farm more land and use more water, there are ways to do it. There's a lot of environmental policy that doesn't allow us to use certain water. And I want to talk specifically like California deltas, Central Valley. There's a whole area that was farmed regularly, and they let all that die because they were protecting some little fish that is in the deltas because they supposedly need the water, or they might get pumped onto the ground for irrigation. My point is, I'm not saying I want to kill the fish. I'm just saying that if you didn't care about that fish, you would have more food production. Okay, so our formula is pretty much this, and this, you've seen various forms of this. Y equals y sub 0 e to the kt, or y sub 0 is the initial amount of whatever you're talking about. If it's a substance, if it's a population, if it's money, that's your initial amount. And then you have your k is your, it's a constant, growth constant. T is time. So that's the basic formula. You may have seen this also in amount equals P e to the RT when we talk about continuous growth of money, like in a bank account, continuous compounding of interest. You might have seen this as P of T equals P sub 0 e to the KT, another formula for population growth. Instead of Y, you use P, but it's a very commonly used formula. Okay. E to that should be here. That's R.
No, I meant on the circle.
That's K.
Okay, thank you.
That's e to the KT. I know it's sometimes they get so small. I'm like, what does it say? Let me make this bigger. Okay, so let's do some problems. This example, they're just showing, they're illustrating the doubling time population after different amounts of time as it grows. And in exponential growth, it's not linear. It keeps growing faster and faster and faster. And it's an interesting conversation. We talk about population sustainability. There was one thing I did years ago. I went to a thing. I didn't do these. I went to a presentation about wild sheep. See about wild sheep before? Have you ever seen a wild sheep? Bighorn sheep. They got the big, really cool. I think the only time I've seen them were actually in Montana. No, I saw them by Walker Lake one time. And what they're telling us is like a mountaintop could maybe support 50 wild sheep, bighorn sheep. And there'd be 100 of them. So it's not like 50 die. It's like they all die because they all eat the resources till everything's gone. So they would take 50 of them and move them to another mountaintop where they all had died or something. So they move those resources around. And I have a friend from Scouts who's a fish and game person. And he said they actually also take them to other states. They'll take them to Idaho in an area where the population died out. Okay, let's talk about bacteria. The population grows according to the function f of t equals 200 e to the 0.02 t, where t is measured in minutes. How many bacteria are present in the population after 5 hours, and how long will it take for it to reach 100,000 bacteria? So The 5 hours is 300 minutes. So we would simply do F of 300 equals 200 e to the 0.02 times 300. It's a 3. And what did I come up with? I came up with 80,686. There's a decimal there, but you round to the nearest bacterium. So it's that non-challenging. It will get more challenging though, so don't worry. Now, the other way to look at this is how long will it take for there to be 100,000? Obviously, it's going to take more than 5 hours because it's 5 hours, you're at 80,000. So you could take that 100,000, set it equal to the 200 e to the 0.02 t. And then if you divide by 200, 100,000 divided by 200, come up with 500. 500 equals e to the 0.02 t. Okay, so here's where your 126 skills come in. How do we undo something with an e as the base? Natural log, very good. So the natural log of 500 equals the natural log of e to the 0.02 t. And this part cancels or undoes itself. So it's natural log of 500 equals 0.02 t. And now from your algebra skills, how do you get that t by itself? Divide by 0.02. So t is the natural log of 500 divided by 0.02, and that comes out to be 310.73 minutes. It's funny that I wrote it there. It has a lot of sideways movement. Okay, that's it. Let's go ahead and do any questions about this whole process, what we just did? You. Yes, go ahead.
So what were we doing when we got the 80,686?
So that one, we're just told how much after 5 hours. So they say 5 hours, it's in minutes, so 300 minutes. So we plug that in. That's finding the population after so much time.
Okay.
And the second part is how much time to get to this population.
Okay, thank you.
Sure. And we're going to do another example like that, if you'd like, to reinforce that. Here we go. Consider a population of bacteria that grows according to the function f of t equals 500 instead of 200 e to the 0.05 t, where t is measured in minutes. How many bacteria are present in the population after 4 hours, and then when will it reach 100 million bacteria? I've asked my biologist colleagues, how do they count these? I think it's where they take like a picture of it and a computer counts it up for them. So, but there's not someone sitting there counting it, but it's this part. I mean, even 100 million to count that up, how long will it take a machine to count that? It'd be a long time, wouldn't it?
Mhm.
Is it counted like 1, 2, 3, or is it like counting 1,000 every second? I mean,
Well, that identifies just the basic structure of the bacterium, and then it can go from there and just count them all at once, which is the structure of it.
but you have to go from a photo. I don't know how to say this. It seems like you have to go from the multiple steps where it's reading an image, processing the image, and then doing the calculation. So how fast is that? Is it still,
Interesting to know.
huh?
It'd be interesting to know.
I didn't know if you were in the biology field, so if you knew all this.
A little
Ask your professor. Okay, so 400 minutes, or sorry, 4 hours is how many minutes?
140.
So 240 equals 500 e to the 0.05 times 240. What do you get for that? And when you're doing the power, make sure you put the power in parentheses. If your calculator doesn't automatically go up for exponents, so do it in parentheses. Okay, so what do you get for that first one? Yeah.
1,977.
That's what I have. 81,377,395.71. So we'd round that to 396. 81,377,396. Now the next question is, how long to get to 100 million? It's a lot of zeros, and to think they're voting to give 4 billion to Ukraine. I'm not making a political statement or judgment there. It's a lot of money. Okay, so here's our setup for the next part. 100 million is 500 e to the 0.05 t. So what do we do with that? Divide by 500 first. So I did this, I got 20,000. E to the 0.05 t. Let me just check my math because I almost feel like. Is it 200,000?
That's what I got.
Okay. So I'm off by a 0. By magnitude of 10. Okay. Now what are you going to do? Take the natural log. So natural log of 200,000 equals 0.05 t. How do I get the t? Divide by 0.05. So t equals what? And that is approximately what? Minutes. Pretty crazy that it can go from 81 million. I guess it's 4 minutes later. It goes from 81 million to 100 million. That's the nature of exponential growth, right? That's one of the dangers of. I mean, there's a pretty dark side. I don't want to get too depressing here. But like cancer is like that. I mean, so you get an aberrant cell, and it grows and doubles and doubles and doubles, doubles, and it starts real small. And if you don't check things out, you notice later on. the big example I was given, like, okay, 20 years ago, what was I doing in the sun? So if I got a bad sunburn, that could start the process then that I don't know for 20 years. So I keep checking, like, okay, how old was I then? But did I start to use sunblock on a regular basis? So I think I'm in the clear now, but you never know. Okay, questions there before we go on? You can do that on your own, the homework, I assume, okay. Okay, let's go ahead and talk about money. So well, if you wanted to read through this part of the book, they're talking about compound interest formula that you might have seen before, like the old-fashioned amount equals principal times 1 plus r over n to the nt power. And if you take that formula and if you take it as n goes to infinity, there's a little bit different, there's a limiting process for that. You end up with, so you get this formula here, and you end up with E coming out of this calculation here, which leads us to the formula, the amount equals P e to the RT. So I'm going to just hit on that for a second. A student of mine recently asked where did E come from, and I came up with 3 definitions for E, and this is one of them here. The limit as m goes to infinity of 1 plus 1 over m to the m power. That's one of them. There's also an infinite sum you can do for E. And there's a third one. I forget, I don't recall that one right now. So this is what I remember when I was a student learning that formula, and I'm like, oh, there is a shampoo called Pert. Who's heard of Pert shampoo? Pert Plus. Okay. So that used to stick with me. I don't use Pert though now. Okay, 25-year-old student is offered an opportunity to invest some money in a retirement account that pays 5% annual interest compounded continuously. How much does the student need to invest today to have $1 million when she retires at age 65? What if she can earn 6% at the same interest compounded continuously? So the goal is, this is the amount at the very end. So we want to know what the now amount is, the current investment amount. And I'm going to be honest, this isn't quite the way it would actually happen. This is a fun exercise to do, but we'd probably do a sinking fund or an installment fund with a goal in mind. So if you want to learn more about that, I teach a Math 120 class sometimes. I get to teach in the fall though, which is exciting. Okay, so again, we're going to go amount equals P e to the RT. So the amount, the goal is $1 million, $1 million. P e to the 0.05 T. Now, what is T in this case? She wants $1 million at age 65, and she's 25 when she starts. So how many years is that? 40 years. Now, let me be clear. So this is a number here, and this is a number here. P is the only variable in this process.
How did you get 40?
40 because it's from age 25 to 65.
Oh, okay. Thank you.
No problem. And I'm going to give you a little plug here too while we're talking about investments. So I have a hard time not talking about this. The sooner you can start, even doing $10 a month into a retirement type account, the sooner the better. And it helps later on in life. It grows. It grows really well. So, of course, it doesn't help when the stock market's down 4,000 points as it is right now. And I don't look at my stuff. I've not looked at any of my accounts since everything crashed. So I'm like, it'll come back. It's always going to be up in the end. Okay, but my point in underlining these things, that this was a number, that's a number, so we can divide by the e to the 0.05 times 40. And then we end up with the principal to start with is 1 million divided by e to the 0.05 times 40. So what would that be? What do you get? And part of this is an exercise in knowing that you put it in your calculator correctly, and that's not a judgment or criticism. It's just easy to make a calculator mistake here. You may have the math down to a T. It's just getting it into the machine is what's important. And that is one of the reasons that it's a blessing and a curse. The TI-80, the newer one, this is the TI-84 plus CE, Python edition. I don't know what that means, but when I hit the caret button, it actually shifts up and fills things in. Other calculators I've had, other older models, you hit the caret button, then you got to make sure you have a parenthesis because otherwise it'll raise the first thing and then multiply the result by the second number. So I'll just tell you my number is $135,335.28. So how many students at 25 have $135,000 sitting around to invest? Probably not a lot. That's why I think it's, if you can jump into even 10, 20 bucks a month, get into a regular investment cycle. I know that when I was a young teacher right out of college, there's a company, Invesco, did a program like that with our school district. And I really wanted to have the money to put into it, but I did not have the extra $100 a month even to put away. So you do what you can when you can. So let's see, the other one asks us to at 6% interest, e to the 0.06 times 40. And so we divide by e to the 0.06 times 40. So our P is what? I got 90,717.95. So if you're not getting this number, please let me know. I'll come around, look at your calculator, see how you're putting it in, and make sure we got any bugs debugged. So obviously, if you had a higher rate, less money has to go in to get this up there, but rates like that can be pretty challenging when the Fed has the rates down so low. And this is the thing that people don't quite get is like a high Fed rate means you can have higher interest rates for savings, but you're gonna have higher interest rates than that for borrowing. I think that my first car was like 7% interest rate, which is like, oh my gosh, what happened? But the Fed had a higher rate back then. So, and I'm sure my credit wasn't as good then. Suppose there's a big typo in here. I don't know what happened with this part, but suppose instead of investing at 25, the student waits until 35, how much would she have to invest at 5% and 6%? So again, we have the $1 million. Equals the principal times E to the 0.05 times, now it's 30 years instead of 40 years. Yes, bless you. Sorry, I was focused on the math. So here to get it to grow. No, I don't know why I keep doing more work than I need to. I can go up to the previous submission and change that to 30. Okay, so at 30 years at 5%, I come up with $223,130.16. And we have 30 years at 6%. This is a tool, most of your calculators will have this. So you can go up and highlight the previous entry and just change what you need to change. I'll change that to 6%. And for that one, I get $165,000, $165,298.89. Okay. Okay, there's another one here I want to look at. And there's a concept I want to talk to you about briefly. I'm not going to dwell too much on it. I just find these type of things interesting in my wheelhouse, sort of my wheelhouse. Okay. How much needs to be deposited now into an account to obtain $4,500 in 13 years at the interest rate is 3% per year compounded? So same thing, same formula. The amount equals principal times e to the RT. What's the amount that we want to have? What's our target? 4,500. What's our current amount? We don't know. And then we have e to the, what's the interest rate? 0.03, and the time? 13 years, yeah. So what do we have? Okay, tell me what you have. I got 3,046.76. Do we agree? Anyone else do this? Okay. So like I said, rates are really low right now, still relatively low. I know they just had a big rate increase, like a 0.5% increase, which is one of the big reasons the market's down so many thousands of points lately. And it's that will have an effect that interest rates on savings accounts will go up a little bit. I was at the bank yesterday and the guy was telling me, hey, maybe you should convert this savings account to a money market account. I'm like, well, I want the savings to be safe. And he said, our money markets are safe. Okay. So, okay. What I want to also hit on is this concept of doubling time. So let me just, if you don't mind, well, I guess this does it pretty well right here. If you're going to double what you started with, that means you can divide that initial amount out. You have 2 equals e to the kt, taking the natural log of both sides, natural log of 2 equals natural log of k, or equals kt. So to get the time to double, it's going to be natural log of 2 over k, where k would be your rate. So if in a money situation, a doubling of money, it's going to be the natural log of 2 divided by whatever the interest rate is. So this is just a side topic, and this is something that you may hear at some point called the rule of 72. Has anyone ever heard of the rule of 72? No? Okay. I probably heard about the first time when I started teaching Math 120, to be honest with you. And it talks about the rule of 72 is the doubling time of if you invest something at whatever percentage, you divide 72 by that percentage, not in decimal form, but in the percent form. And then that's how long it takes to double. So for example, an easy one is saying, okay, if you have 8%, 72 divided by 8 equals 9. It means it'll double in 9 years. Now, the reality is it's not the rule of 72. 72 was chosen because it's a more conservative estimate and it has more factors. Can someone take their calculator and punch in natural log of 2? What's natural log of 2?
0.693147186.
So 0.69, if I stop there, it should be the rule of 69. And that would be you divide whatever your, you divide 69 by whatever your interest rate is, and that'll give you the doubling time. So it's less conservative that way and has fewer factors, but it should be the rule of 69. And I've gone around circles. There's a guy in my extended family who's pretty well off banker person. And we would argue about the rule of 72 and what it really is. And he would never accept that it's really the rule of 69. So doubling time, and this isn't just for money, but even for populations, the calculation is natural log of 2 divided by the rate of growth. If it's an interest rate, if it's a population growth rate, or so on. But this formula has some other implications. Assume a population of fish grows exponentially. So we can assume an exponential growth in the population. A pond is stocked initially with 500 fish. After 6 months, there are 1,000 fish. So it went from 500 to 1,000 in 6 months. So that's the doubling time is 6 months. The owner of the lake will allow his friends and neighbors to fish the pond after the fish population reaches 100 or 10,000. When will the owner's friends be allowed to fish? So assume the same rate of growth with this. So assume that the population won't be capped by the resources of the lake. So what we have is our time equals the natural log of 2 divided by K. We want that K. So how long did it take for it to double? 6 months. So 6 equals the natural log of 2 over K. If you multiply both sides by K, 6K equals the natural log of 2, and divided by 6, K equals the natural log of 2 over 6. And the book tend to leave this in terms of that expression instead of getting a decimal, but I'm good either way. These are all estimates anyway. So now here's our goal. Our goal is 10,000 fish equals the initial 500 fish times e to the k. K is natural log of 2 over 6 times t. T is time. So everything there except for the t is a constant. Okay, what are we going to do with that 500? Divide it out. And 10,000 divided by 500 is 20. So 20 equals e to the natural log of 2 over 6. It's not 6, natural log of 2 divided by 6 times t. And now how do we get rid of the e? How do we bring that power down? Natural log, very good. Natural log of 20 equals the natural log of e to the natural log of 2 over 6 times t. This part cancels. So it's natural log of 20 equals the natural log of 2 over 6 times t. Then we can divide by the natural log of 2 over 6. So our t is natural log of 20 over the natural log of 2 over 6. Oh, I guess algebraically or mathematically, we could write it like this: 6 times the natural log of 20 over the natural log of 2 means the same thing. So how much time would that be before they can start fishing, pulling those fish out of the water? What do you come up with? Yep. 25.93 months. So approximately 26 months. Okay. Who here likes to fish? One person. Okay. Have you ever fished Lahontan?
Well, actually, I have. We didn't, they released it.
Yeah.
We don't want to lose that fish.
The last president and he'd take me out to Lahontan to go fishing. He had it all set up. He knew how to do it. And I think we caught 25 carp, but they all released. And they're big. They're like this big. Okay, let's try another one like that, talking about population doubling. Same problem, but now it's 9 months for the fish population to double. So if that's the case, if it takes 9 months instead of 6 months, how long will it take? So our time is going to be the natural log of 2, no, over k. Yeah, so I'll leave that. So it's 9 equals natural log of 2 over k, or 9k equals the natural log of 2, or k equals the natural log of 2 over 9. So this will be our k when we do this calculation. And again, we're waiting for 10,000 fish equals 500 fish, e to the natural log of 2 over 9 times t. What's the next step? Yeah. So that would be 20 equals e to the natural log of 2 over 9 times t. Now what are we going to do? Take the natural log of 20. It's the natural log of e to the natural log of 2 over 9 times t. So the natural log of 20 equals the natural log of 2 over 9 times t. And now what? So t would be 9 natural log of 20 over the natural log of 2. And what would that be? Anyone know with the calculator? What's that? Good, 38.9. Okay, good. You say here that you're not supposed to eat the fish in Lahontan because of the mercury. I don't know how serious that is, but
I wouldn't want to eat the fish anyway. The water's not that pretty.
any questions there before I go on? Place I drove by recently, actually Sunday, Mono Lake. I drove by Mono Lake. And I remember it being blue or water. It was green. It was green. And I'm like, what's going on with this? Because I thought that the brine in the water would have kept it from growing algae, but it was really green. Okay, last problem for this section. Find the time it takes for $7,000 to double when invested at an annual rate of 18% compounded continuously. And they're going to find the time it takes for $700,000 to double. So what we can do is we can go the whole long way of saying that, 14,000 equals 7,000 times e to the 0.18 times t and work on it that way. But we have that formula, the doubling time is natural log of 2 over k, in this case, is 0.18. What's that going to be? I have 3.85 years. That's a fast doubling time. And, it really doesn't matter if you start at 7,000 or 700,000. It's still going to double in that time period if you have that kind of rate of growth. Okay, that's exponential growth. Typically a fun topic, especially when we talk about money. It's fun to dream about money. And then we'll talk about the K now.